So here's a short video that explains how to perform the equilibrium lab. I took atmospheric pressure and also room temperature, filled the sink with water that's at room temperature, filled a 250 ml graduated cylinder with water and inverted it so that the open end is just below the surface of the liquid in the sink, and clamped it there. Now I've got a piece of PVC tubing that you can see running down the side of the graduated cylinder. It's held in place by a couple of elastic bands. At the bottom of the tubing I have a bent piece of glass in a U shape, so it directs all the gas up into the cylinder so none will escape. And that PVC tubing is connected to the side arm of a 2-neck adapter. The 2-neck adapter is mounted in a 50 ml RB flask, which contains a mag stirrer. And of course that's sitting on top of a mag stir plate. On top of the 2-neck adapter is an addition funnel. Now to begin with, I remove the addition funnel and I deliver 5 mils of a solution of potassium bicarbonate, it was about 2 molar I used, into the bottom of the RB flask, right down through the 2-neck adapter into the RB flask. While the pipette is draining, I deliver 5 mils of distilled water into a 10 ml graduated cylinder, and I'll use that water as a rinse at the end. Then I connect the addition funnel. I ensure that the fittings are tight and leak-proof and that the valve on the addition funnel is closed. And pipette 5 mils of an acid solution into the addition funnel. If you're wondering why the water is dripping in the sink, it's simply because I want to keep a constant water level in the sink, and the standpipe is not completely watertight. So I've cut the video here and raised the camera so you can see the top of the addition funnel. Now take a rubber bulb. I took the tapered silicone piece off the bottom of a squeeze bulb, and that particular bulb happened to fit nicely, snugly in the top of the addition funnel. The reason is when you open the stopcock to allow the acid to flow down into the system, it simply won't drain because the capillary in the stopcock is just too narrow to allow liquid and air to exchange. And so you need the squeeze bulb to apply a small amount of pressure to force that liquid down into the flask. So I start the mixer, and then I start the timer. Then I open the valve on the addition funnel and liquid does not drain. You say, well, of course not. I've got the top of the addition funnel plugged with the bulb. Well, that's true, because if I didn't, some of the CO2 gas that's evolved would escape out of the top rather than all being forced into the graduated cylinder. One word of warning here. Don't squeeze the bulb hard or you'll drive air right through the entire system into the graduated cylinder, likely invalidating the results. So just a gentle squeeze, just enough to push the liquid through the valve. So you notice that I squeeze and release the bulb before closing the valve. Don't close the valve until after you've released the bulb, because you want to bring the pressure inside the funnel the same as it was before squeezing the bulb. You see the carbon dioxide gas being evolved and collected. Don't delay in putting the 5 mils of water in. Then resecure the bulb, open the valve, and use some pressure on the bulb to squeeze that water into the system, and remember to release the bulb before you close the valve. And it works. So now you want to record the volume of gas collected at 1 minute intervals. Rather than lowering the graduated cylinder into the sink so that the level of liquid in the cylinder is the same as the level in the sink, so that the pressure in the cylinder is the same as atmospheric, rather than that, it's easier, I think, to measure the height of the liquid column with a ruler in centimeters of water, that is the height in the graduated cylinder above the level in the sink, and convert that height in centimeters of water to a pressure difference in millimeters of mercury. And that's pretty much it. You just have to refill the cylinder and clean the glassware, and you're ready for the next run. The equilibrium constants calculated for the monoprotic acids came out surprisingly close, actually spot on with what would be predicted from the pKa and the pKb of the combined acids. So despite some bumps along the way, it looks quite promising as a method. One thing I did not appreciate at the time is the importance of ensuring the final concentration, the final mixture, is acidic, because carbon dioxide is an acid gas and it would be held in solution and converted to bicarbonate if the solution is basic. And we want to make sure it's all released, so hence the final solution pH should be, I'd suggest, less than 5 or 4. The next step is to use the rate of evolution of CO2 gas to see if we can determine the kinetic order of the reaction and the rate constant. And that about does it, so thanks for watching.